Hello students, welcome to MEC 1321 Engineering Statics. I'm Dr. Stewart, and today we're going to cover Chapter 8, which is friction. The objectives that we have for Chapter 8 are to introduce the concept of dry friction and show how to analyze the equilibrium of rigid bodies subject to this force, and to present specific applications of frictional force analysis. So today we're going to go over, for Chapter 8, we're only going to go over Sections 8.1, which is characteristics of dry friction, and we're going to go over Section 8.2, problems involving dry friction. So let's go ahead and get started with Section 8.1, characteristics of dry friction. So the first question is, what is friction? Friction is a force that resists the movement of two contacting surfaces that would slide relative to one another. So if you have two surfaces that are in contact, if they are not moving, there is a frictional force that prevents them from moving, from sliding relative to each other. Now, dry friction, also sometimes called Coulomb friction, is a friction that occurs when there is no lubricating fluid. So dry friction is when you have a dry surface. So let's kind of go over the theory of dry friction. Let's try to understand what are the forces that develop due to friction. What is a frictional force? In order to do that, let's first consider a block that is resting on a table. And this block that is resting on a table has an applied force P that is applied to it at some distance h. So there is a force P that is applied at some distance h from the ground. It also has a weight that is applied at the centroid of the block, a weight called W. So we have this contacting surface. We have the block, and there's a contacting surface. And we know that in order for the block to not move, for it to remain at rest when there is an applied force P, that there needs to be some kind of frictional force, F, that resists the force P, the applied force P, in order to maintain equilibrium. We also know that there must be some kind of normal force, N. And this is a force that, this normal force is a force that prevents the weight from going through the table. So it's the normal force is a support reaction, and the frictional force F is a force that arises, the frictional force, to prevent a translation in the x direction. Now both of these forces are applied at some distance x. And that distance x is necessary in order to maintain equilibrium if we were to do the sum of the moments. So what we can do is we can take this block and create a free body diagram describing the dimensional information of each of these points of interest. So what is the position of the weight, A over 2? What is the position of the applied force P? It's H. What is the position of X and the frictional force F? It's at a distance X, okay, from point A. So we have our free body diagram. We've identified the positional information for each of these given forces and for the unknown forces. And now what we need to do is we need to balance. We need to apply our equations of equilibrium. Now, to maintain equilibrium, it is necessary to balance the tipping effect caused by the applied force P about position O, where we identify position O as a location at which the frictional force and the normal force are applied, right? When we consider the moment about point O, then we'll note that the frictional force and the normal force will cancel out because their line of action goes through point O. However, the applied force P and the weight still appear in our moment equation. And so when we apply the sum of the moments, assuming counterclockwise is positive, we'll find that our sum of the moments about point O is equal to W times X minus P times H equal to 0. So thus, the moment equilibrium equation gives us the position x of our frictional force and our normal force, where the position x is equal to the applied force P times its position h divided by the weight. So now let's go into the types of dry friction that exist. So let's first talk about static friction or impending motion. Impending motion is the case where motion is imminent. It's imminent such that the frictional force attains a certain maximum value, and that maximum value is called Fs. So Fs is the limiting static friction force. This is the force value that when exceeded, or the force value that when exceeded will lead to motion, will lead to the body being in motion. So we're at an equilibrium point, or the point where motion is imminent. And this is the maximum value, or the limiting static frictional force, the maximum value that static frictional force can be. And it's described as the limiting static frictional force, Fs, is equal to mu s times n, where mu s is the coefficient of static friction and n is the normal force. So once we've been able to calculate that, we can directly put in this Fs into our free body diagram. Now when we do that, we can also find the sum of the surface reaction. So what is the resultant reaction force at the contacting surface between the block and the flat plane? Well, in order to find that resultant reaction force, Rs, we can simply sum the Cartesian vectors for Fs and for the normal force n. So it's very important to understand what impending motion means. Motion being imminent, but motion not occurring. In addition to be able to find the magnitude of the reaction, in addition to finding the Cartesian form, we can also describe the angle of static friction. So the angle of the reaction force relative to the y-axis, where that angle is equal to tan inverse of the limiting frictional force divided by the normal force, which is equal to tan inverse mu s times n divided by n, which is equal to tan inverse mu s. So now let's look at another type of dry friction, which is kinetic friction. Kinetic friction is a friction under motion. In this case, if the magnitude of the applied load, of the load that is applied, exceeds the limiting static friction force, so if we're no longer in equilibrium, if force P is greater than the Fs, limiting static friction force, then we know that motion is going to occur because our equation of equilibrium has been violated. And when this motion occurs, the value of the frictional force drops to a value of Fk, which is called the kinetic friction force. This kinetic friction force is found to be equal to mu k times n, where mu k is the coefficient of kinetic friction. Using a similar approach, we can find the resultant reaction force of the resultant reaction force Rk, which is equal to the sum of the Cartesian for the force for the kinetic frictional force plus the normal force, right? And we can also find the angle of kinetic friction using a similar equation, where the angle of kinetic friction is equal to the tan inverse of the coefficient of kinetic friction. Now, it's important to note that when we transition from static friction, where we have a frictional force which is equal to the applied load, when we transition to kinetic friction, where the applied load is greater than the limiting static friction, and thus we have a kinetic frictional force, we'll find that the value of the kinetic friction force is smaller than the value of the limiting static friction force. And this is because as motion occurs, the surface between the surface between the two contacting surfaces will degrade. The actual contacting surfaces will degrade, and the frictional coefficient will decrease, leading to a lower value of the kinetic friction force. So it's very important to remember that our kinetic friction force is typically less than or equal to our static friction force. So let's actually go ahead and look at a diagram. If we were to craft a diagram which relates the frictional force F with the applied force P, then from the value of the frictional force from less than P up to the value of P, we have no motion, right? So for a majority of the life here, there's no motion, no apparent motion. At the peak, where the force, the limiting static frictional force is reached, we have impending motion, where if the force P exceeds the value of the frictional force, then we move into motion, right? And then from beyond that, when the value of P is greater than the frictional force, we have motion. And notice that when the value of P is greater than the limiting static frictional force, then the value of the kinetic frictional force decreases significantly. And that's due to the degradation of the contacting surface. Okay? So in general, there's three different states that we're going to study. There's a state of no apparent motion, where we know that the sum of the forces are going to be equal to 0 because there's no motion. We know that the value of the frictional force, the value of F must be equal to P to maintain equilibrium. And we know that the value of P, the applied force, is less than the limit in static friction, right? So there's some frictional force F that exists when there's no apparent motion, and it's equal to the value of the applied load, but we also know that P, our applied load, is less than our static frictional force. Then we have the state of impending motion, that critical point, where again we still have a state of equilibrium, so the sum of the forces is equal to 0. However, we find that the friction force F is going to be equal to the applied load P, and both of them are going to be equal to the limiting static friction force, which is our critical value, about which we're either in motion or not in motion. And then finally, we have motion. And this is the point where we no longer have an equilibrium state. The sum of the forces is no longer equal to 0. And that's because we have motion. We have some kind of motion, right? And we find that the value of P, our applied load, is going to be greater than the value of our limiting frictional force. We're also going to find that the magnitude of the kinetic frictional force is less than or equal to the limiting static frictional force. Okay? So it's very important to be comfortable with understanding what F is, what P is, and what Fs and Fk are, and how we can identify if there's apparent motion, impending motion, or motion. I mean, if there's no apparent motion, impending motion, and motion. Now, it's very important when we're given a problem to be able to identify exactly what the problem is asking us for. So there will be certain key words that you need to note to identify if there is going to be impending motion. Impending motion means about to happen, imminent, soon. When you hear things such as on the verge of, close to, beginning to, about to, then you can assume that the problem is asking you or telling you that it's a condition of impending motion. And so you're going to need to use the following relationship, where the frictional force is equal to the limiting static friction, right? So now let's move into section 8.2, which is problems involving dry friction. And so this is where we kind of learn more about, what are some of the types of problems involving dry friction, and how do we identify an approach to actually solving those problems. So one of the easiest and the most classic types of problems is a problem where there is no apparent impending motion. So a problem where there is no motion, there's no impending motion, and it's strictly an equilibrium problem. So let's assume the case of a box that is on a surface at an angle. And we can draw our free body diagram where we have our weight the weight applied at the centroid. We have some applied force P, which is along the direction of the wedge. We have a frictional force, and we have a normal force, which is applied. Frictional force and a normal force. In the case of this type of problem, it's strictly an equilibrium problem, where the number of unknowns must be equal to the number of equilibrium equations. The frictional force must be less than or equal to the value of the limiting static friction force Fs, right? So in this case, we know that there's no impending motion at any of the surfaces, and we apply our equations of equilibrium, and our number of unknowns should be equal to our equations of equilibrium. So a problem such as this would ask for you to calculate the value of the frictional force F for a problem. So calculate the value of the frictional force F for a problem where there is no apparent motion, right? Now another case is the case where we have impending motion. In particular, well, let's continue with the current case that we're dealing with. So in the case of no apparent impending motion, first we have to identify if there is going to be impending motion or not, right? So first we need to draw our free body diagram, we need to craft our equations of equilibrium, and then we need to determine what the value of the force F is. And we need to determine if force F is less than or equal to the limiting static frictional force. If it's less than, then that's great. If it's equal to the limiting force, then that's fine. But if we're unable to find an equilibrium state, then that means we're in motion. And this problem is a problem that we would need to use a different approach to solve. Now let's move into the case of impending motion. In particular, impending motion at all points of contact. In this case, let's draw a diagram where we have a ladder which is leaning against a wall. And there are 2 points of contact, point A and point B. And both of these points of contact will have some kind of frictional force that resists the motion of the ladder. Now, in order for this body to have any motion, it's required that both point A and point B have impending motion, because point B cannot move unless point A moves, and point A cannot have any motion unless point B moves. Both points must move simultaneously. In this case, we have impending motion at all points of contact. For this type of problem, the number of unknowns are equal to the number of equilibrium equations plus the total number of frictional equations, where motion is impending when the frictional equation is equal to the limiting frictional force equal to the coefficient of static friction times the normal force, right? So in this case, for this 2D problem, we have 3 equations of equilibrium, and we have 2 frictional equations for point A and for point B, respectively. So we have 5 equations, and the number of unknowns should be equal to that number to those 5 equations. It cannot be greater than. And so we simply find our equations of equilibrium, identify our frictional equations for the 2 points of interest, and then we attempt to solve for our unknowns. The final type of problem is impending motion at some points of contact. And this is the case where you have multiple points of contact, but motion can be found in one point of contact and not in another. For the example of this, we have a pin connect, two members that are pin connected on a smooth surface. Both have a point of contact with that surface, a point A and a point B. However, point B is free to move with point A not moving. Because this is a pin connection, that pin can rotate freely. So if point B moves, the member will rotate, but point A does not necessarily have to move. Same thing vice versa, where point A can move and point B can still be fixed. In this case, we have impending motion at some points of contact. So the number of unknowns is less than the number of equilibrium equations plus the number of available frictional forces. So we have a small set of unknowns and we have many equations of equilibrium and available frictional equations. So there exists several possibilities for motion or impending motion exist. And in this type of problem, we must determine the kind of motion that will occur. So we have to decide, is point A going to have motion or will point B have motion? And this is a very difficult problem in order to solve, to try to identify which of these points of interest will violate the limiting static friction and cause a kinetic friction to occur, to cause motion to occur. So it's very important for you to be comfortable with being able to solve any of these three types of problems involving dry friction. And it's going to be very important for you to do examples from the book in order to build your confidence in solving problems of friction. So now let's kind of look at some basic factors that influence the coefficients of friction. So I've built here a table which describes the type of contact surface and average values of the coefficient for static friction. So when we have metal on ice, you find a mu s ranges from 0.03 to 0.05, which is a pretty small value. And again, remember that our frictional force is mu s times n, right? So if we have a very small value of the coefficient of static friction, then our frictional force is going to be very small. There's very little friction. So metal on ice is a very low friction state, right? It's a very low friction. Wood on wood, however, has a much higher coefficient of static friction, between 0.3 and 0.7. And then aluminum on aluminum has a very high, compared to the others, coefficient of static friction, which is 1.1 to 1.7. So the variables that influence the value of the static friction include the roughness of the material, the cleanliness of the contact surface, the types of, if there exists some type of lubrication, some kind of layer of lubrication between the surfaces. Those all influence the coefficient of friction, the amount of frictional force that develops between two contacting surfaces. So let's now go into the procedure for analysis. How do we actually solve problems of dry friction? So procedure for analysis. The first thing we need to do is, of course, draw a free body diagram. Draw the necessary free body diagrams, and unless it is stated in the problem that there exists impending motion or slipping occurs, always show the frictional forces as unknown, right? So if we don't have impending motion, or if we don't have slip, so if it doesn't say on the verge of, close to, beginning to, if it doesn't have that language which indicates impending motion, then we should just assume that we have some frictional force F that we need to find, and do not apply the mu Sn or the mu Kn equations, okay? Once we've done that, then we need to determine the number of unknowns and compare this with the number of available equilibrium equations. If there are more unknowns than equations of equilibrium, it will be necessary to apply the frictional equations at some, if not all, of the points of contact to obtain extra equations needed for completing a solution, right? So we've listed the number of unknowns. So we have whether it's the supports, and then we have so the supports, and then the values of the frictional forces, just the F frictional force FA, FB. We evaluate to see if we have the correct number of equilibrium equations for the number of unknowns. If we don't, then we need to identify what type of problem is it. Is it a problem of impending motion at all points of contact, or is it a problem of impending motion at some points of contact? And from that evaluation, we'll be able to determine, okay, where do we need to apply our frictional equations F, mu, n at which points in order to in order to have enough equations for the number of unknowns that we have. If the equation F equal to mu n is to be used, it will be necessary to show F acting in the correct sense of direction on the free body diagram. So it's important for us to use the sense inspection method, right? Where we assume, okay, if we were to do the sum of the forces in this direction, the frictional force must be in the opposite direction to maintain equilibrium, right? So the same stuff that you applied in the method of sections in chapter 6, you'll need to use in order to assume the appropriate sense for those frictional forces. Now let's move into the equations of equilibrium and friction. So we need to apply the equations of equilibrium and the necessary frictional equations or conditional equations if tipping is possible, and solve for the unknowns. If the problem involves a three-dimensional force system such that it becomes difficult to obtain the force components or the necessary moment arms, then we need to apply the equations of equilibrium using the Cartesian vector form, right? And that's pretty much how we solve these problems. So the most difficult part of problems of friction is being able to identify the type of friction problem that exists, to identify if there is no apparent motion, if there's impending motion, or if there is motion. And the only way to really develop this skill is through practice, through solving several problems that have these different types of situations, and developing a sense, a personal sense of and a personal methodology on how to identify their type and solve the problems effectively. So with that said, I suggest that you read Chapter 8, Sections 8.1 and 8.2. Definitely try to review the example problems. Get yourself familiar with the example problems. It shows, in the example problems, it should show problems of no motion, impending motion, and motion. And this will give you a good idea of the methodology. Definitely read the solution for the problems. Don't just look at the equations, but actually read the description of the solution, which should help you understand how to identify the different types of motion. And come prepared for a quiz on dry friction, where you'll be asked to identify the type of friction and apply the equations of equilibrium and frictional equations in order to solve for the unknowns. With that said, thank you for your time. If you have any questions or concerns, you can send me an email, or you can post a comment on this video, and I'll definitely get back to you. I'll see you guys next time.